There is a planet in our solar system so large that all the other planets combined could fit inside it with room to spare. It has a storm that has been raging continuously for longer than human civilization has existed. Its gravity is so powerful that it acts as a gravitational shield for the inner solar system, deflecting or capturing asteroids and comets that might otherwise strike Earth. It is the oldest planet in the solar system, the first to form after the sun ignited. It is a failed star, a world of liquid metal, a place where the atmosphere has no floor, where the pressure gets so high that physics behaves in ways nothing on Earth can replicate. You know this planet. Everyone knows it. It is Jupiter, the king of planets, the largest object in the solar system other than the sun itself, the giant that has loomed over astronomy since Galileo first pointed a telescope at it in 1610 and saw 4 moons circling it, delivering the first concrete proof that not everything in the heavens revolves around Earth. And almost everything you think you know about it is either wrong, incomplete, or so much more complicated than the version you learned that the simplified version actively misleads you about what Jupiter actually is. There is something particular about the way Jupiter gets taught and talked about that produces this problem. Jupiter is genuinely dramatic. It is enormous. It has a famous storm. It has dramatic moons. It has a magnetic field that would extend past the moon if it glowed visibly in the sky. So there is a temptation to let the drama do the work and skip the precision. The result is a collection of arresting claims: failed star, protective shield, permanent storm, simple gas planet, that are memorable and striking and mostly not quite true. The reality of Jupiter is more nuanced, more strange, and more interesting than the myths, but the myths are stickier because they are simpler. This video is an attempt to fix that, not by adding more dramatic facts on top of the wrong ones, but by replacing the wrong ones with the actual science, which turns out to be more disturbing and more beautiful than anything the myths offer. Jupiter is not a failed star, not in any physically meaningful sense, and the common claim that it would need to be just a bit bigger to ignite is off by a factor of roughly 80. Jupiter does not protect the inner solar system. Decades of careful orbital simulation have revealed that Jupiter is statistically as likely to send comets and asteroids toward Earth as away from it, and its role as a shield is one of the most persistent myths in planetary science. The Great Red Spot is not a stable, permanent feature. It has been shrinking for over a century and may disappear entirely within decades. Jupiter's core is not a simple ball of rock surrounded by gas. It is a diffuse, partially dissolved, blurry region of exotic mixed material whose structure defies every model that existed before the Juno spacecraft arrived in 2016. The 4 moons Galileo discovered are not incidental details. One of them has the largest ocean in the solar system. One has the most geologically active surface anywhere in the known universe. One may have a subsurface ocean buried under ice, and one is the largest moon in the solar system, bigger than the planet Mercury. This video is not a tour of interesting facts about Jupiter. It is a systematic dismantling of the version of Jupiter that most people carry in their heads, the simplified, textbook, science class version, and a replacement of it with the far stranger, far more complex, far more interesting reality that spacecraft, telescopes, and decades of theoretical physics have revealed. By the end, Jupiter will not just be bigger than you thought. It will be different in kind, a world that defies the categories most people use to understand planets, that challenges fundamental ideas about how solar systems form, and that still, after centuries of observation and decades of direct spacecraft investigation, contains mysteries that no one has solved. Let's take the common beliefs about Jupiter apart, one by one. Chapter 1. Jupiter is not a failed star. The numbers are catastrophically wrong. Let us start with arguably the most common thing people say about Jupiter when they want to sound knowledgeable about it. That it is a failed star, that it just barely missed being a star, that if it had just been a bit bigger, it would have ignited into a second sun. This claim is wrong in a specific and quantifiable way. Let's do the numbers. Jupiter has a mass of approximately 1.898 times 10 to the 27th kilograms, or more usefully, about 318 Earth masses, or about 0.001 solar masses. 0.1% of the Sun's mass. The minimum mass required for a brown dwarf, an object that can sustain deuterium fusion in its core, which is the threshold for the lowest class of stellar-type object. Os ixuina and ixalral o warkun worm uiuiasão, approximately 13 Jupiter masses. Deuterium fusion is not the same as the hydrogen fusion that powers true stars. It uses a rare isotope of hydrogen, burns out quickly, and does not provide sustained long-term energy production. But 13 Jupiter masses is often cited as the lowest threshold for stellar-like fusion of any kind. The minimum mass for a true star, an object that can sustain hydrogen-1, protium, fusion in its core, on an ongoing basis, which is what makes stars stars, is approximately 80 Jupiter masses. Some estimates place it slightly lower, at around 75 to 78 Jupiter masses for the lowest mass red dwarf stars. But the consensus range is 75 to 85 Jupiter masses for sustained hydrogen fusion. Jupiter's current mass, 1 Jupiter mass. Minimum mass for deuterium fusion, the lowest form of stellar-like burning, 13 Jupiter masses. Minimum mass for true stellar hydrogen fusion, approximately 80 Jupiter masses. Jupiter would need to be 80 times more massive than it currently is to become a true star. Not 10% bigger, not twice as big, 80 times more massive. To put this in perspective, if you combined all the planets in the solar system, all 8 of them, plus every moon, every asteroid, every Kuiper Belt object, every comet, you would still need more than twice the total mass of everything in the solar system except the Sun to bring Jupiter up to stellar ignition mass. The claim that Jupiter is a nearly star or a failed star, or that it just missed being a star, is not a slight exaggeration. It is off by nearly 2 orders of magnitude. Jupiter is not close to being a star in the way that, say, a very tall person is close to the height cutoff for a basketball team. It is close to being a star in the way that a mouse is close to being an elephant. Both are mammals, both have mass, both are made of matter. But the quantitative gap between them is not a rounding error. Where does this myth come from? Probably from a combination of Jupiter's large size relative to the other planets, its compositional similarity to the Sun, both are mostly hydrogen and helium, unlike the rocky inner planets, and a genuine physical fact that is often misrepresented. Jupiter is composed mostly of hydrogen and helium, the same elements that fuel stars. This compositional similarity is real and scientifically meaningful. Jupiter is, in terms of bulk composition, more like a star than like Earth. But compositional similarity is not sufficient for stellar ignition. You also need the gravity generated by sufficient mass to compress the core to the temperature and pressure required for fusion. Jupiter's core pressure is estimated at around 40 to 70 million times Earth's atmospheric pressure, and its core temperature at around 30,000 to 50,000 Kelvin. The core of the Sun is at approximately 15 million Kelvin. Jupiter's core temperature is not even 1% of what is needed for hydrogen fusion. It is not slightly short. It is not in the same neighborhood. The fusion threshold requires core temperatures that Jupiter does not approach and will never approach because it does not have nearly enough mass to generate them. There is one more subtlety worth including here. Jupiter does produce more heat than it receives from the Sun. It radiates approximately 1.67 times as much energy as it absorbs from sunlight. This excess heat is not from fusion. It is gravitational energy, the slow compression and contraction of Jupiter's interior over the lifetime of the solar system, a process called Kelvin-Helmholtz contraction that also powered the early Sun before its fusion ignition. Jupiter is, in this sense, still slowly releasing the gravitational energy of its formation. But this is not a stellar process. Brown dwarfs and giant planets all experience Kelvin-Helmholtz contraction. It is not fusion, and it does not bring Jupiter any closer to stellar ignition. Jupiter is cooling slowly and will continue to cool. Over the age of the universe, it will never ignite. The math is not close. Chapter 2, Jupiter does not protect Earth. It's more complicated and more disturbing than that. The second most common thing people say about Jupiter, after the failed star claim, is the Jupiter shield hypothesis. That Jupiter's gravity acts as a protective shield for the inner solar system, deflecting incoming comets and asteroids away from Earth and keeping the inner solar system safe for complex life. The logic seems intuitive. Jupiter is huge. It has enormous gravitational influence. It sits at the outer edge of the asteroid belt. It must be sweeping up the dangerous stuff. This idea was popularized in the 1990s, partly through the work of astronomer George Wetherill, who ran computer simulations of what the inner solar system would look like without Jupiter. His simulations suggested that without Jupiter's gravitational influence, the bombardment rate of Earth-crossing asteroids might be 1,000 to 10,000 times higher than it currently is. The idea that Jupiter is essential for Earth's habitability became embedded in popular science, in books, documentaries, and the general scientific imagination. More recent and more sophisticated simulations have substantially revised this picture, and the revision is not in Jupiter's favor. The problem is that Jupiter's gravitational influence is not selective. It does not push dangerous objects away from Earth and leave the rest alone. It gravitationally perturbs the orbits of everything in its vicinity, and those perturbations can send objects both away from the inner solar system and toward it. Jupiter is simultaneously a deflector and a sender. It knocks some comets and asteroids into trajectories that avoid Earth, and it knocks others into trajectories that intersect Earth. The specific dynamics depend on what type of object you are talking about and where it originated. For long-period comets, comets from the Oort cloud that enter the inner solar system on their first or rare passes, Jupiter can indeed deflect them away before they reach Earth-crossing orbits. In this role, as a deflector of incoming long-period comets, Jupiter provides some net protection. But for short-period comets, comets that have already been captured into the inner solar system by previous gravitational interactions, Jupiter is actually a major delivery mechanism. Many short-period comets have their orbits shaped and continually modified by Jupiter's gravity in ways that keep them in the inner solar system and periodically nudge them toward Earth-crossing trajectories. For asteroids, the picture is complicated further by the fact that Jupiter's gravity is responsible for the existence of the asteroid belt in the form it has today. Jupiter's gravitational resonances, specific orbital distances where asteroids would complete orbits in simple integer ratios to Jupiter's orbital period, destabilize asteroid orbits at those distances, creating the Kirkwood gaps, the emptied zones in the asteroid belt. Asteroids at these resonant distances are regularly kicked into highly eccentric orbits that can become Earth-crossing. Jupiter is not merely neutral with respect to asteroid delivery. It is actively, continuously destabilizing a fraction of the asteroid belt and sending those objects into the inner solar system. In 2010, astrophysicists Kevin Grazier and Jonathan Horner published simulation results that directly challenged the Jupiter shield hypothesis. Their simulations, running millions of test particles through the solar system over long timescales, found that Jupiter was indeed capturing some potentially dangerous objects, but it was also scattering others toward Earth. In their simulations, a solar system without Jupiter did not necessarily experience dramatically higher Earth impact rates than one with it, because the absence of Jupiter's scattering influence worked in both directions. The protection was not nearly as significant as Wetherell's simpler models had suggested. Further work has supported this more nuanced picture. The current consensus is that Jupiter provides modest net protection against long-period comets by deflecting incoming objects before they reach the inner solar system in some fraction of cases, but actively increases the impact hazard from short-period comets and asteroid belt objects. The net effect may actually be slightly negative, meaning a solar system without Jupiter might have slightly fewer Earth-crossers than one with it, once you account for all the objects Jupiter's gravity scatters inward over time. The point is not that Jupiter definitively hurts more than it helps. The point is that the simple shield narrative is false. Jupiter is not a guardian. It is a gravitational bulldozer that moves things around without regard for where they end up. And where they end up sometimes includes Earth. There is a deeper implication here. The rare Earth hypothesis, the idea that Earth is specially positioned and protected by the specific architecture of the solar system, including Jupiter, in a way that makes complex life possible, relies heavily on the Jupiter shield claim. If Jupiter is not reliably protective, one of the key pillars of the rare Earth hypothesis collapses, and the case for Earth's exceptionality becomes correspondingly weaker. The solar system's architecture may not be specially tuned for the safety of Earth in anything like the way the shield hypothesis suggests. Chapter 3: the Great Red Spot is dying. And we don't fully know why the Great Red Spot is perhaps the most iconic feature in the solar system. A massive, persistent anticyclonic storm in Jupiter's southern hemisphere that has been observed for hundreds of years. It is the defining visual identity of Jupiter, that swirling orange-red eye, glaring from the planet's cloud tops like a wound that never heals. Except it is healing. It is shrinking. It has been shrinking for over a century and a half, at rates that have accelerated in recent decades. And it is now approximately half the size it was when modern systematic measurements began in the late 19th century. Whether it will survive the current century as a recognizable feature is genuinely uncertain. The Great Red Spot is an anticyclone, a region of high atmospheric pressure rotating counterclockwise in the southern hemisphere at speeds of up to 432 kilometers per hour. It sits at approximately 23 degrees south latitude and has been continuously tracked since at least the 1830s. The first observations that might represent the Great Red Spot are even older. The Italian astronomer Giovanni Cassini described a permanent spot on Jupiter in the 1660s. But whether Cassini's spot is the same feature as the modern Great Red Spot is uncertain. There may have been a gap in reliable observations in the early 18th century that corresponds to a period when the spot was not visible or had temporarily faded. What is certain is that when systematic measurements began in the late 19th century, the Great Red Spot was enormous, approximately 40,000 kilometers in the east-west direction, wide enough to fit 3 Earths side by side. By the mid-20th century, it had shrunk to about 25,000 kilometers. By the early 21st century, it was approximately 16,000 kilometers. As of the most recent measurements in the early 2020s, it is approximately 14,000 to 15,000 kilometers across. The spot has also changed in shape. It was originally elongated in the east-west direction, a classic oval. As it has shrunk, it has become rounder. Its color has fluctuated, sometimes deep red, sometimes pale pink, sometimes almost white, reflecting changes in the chemistry of its atmosphere and the depth of the features it is sampling. The reddish color is thought to come from organic compounds or sulfur compounds brought up from deeper in the atmosphere by the storm's updrafts, but the precise chemical identity of the red chromophores remains disputed. In 2019, the Great Red Spot underwent what observers called a flaking event. Large chunks of reddish-orange material appeared to tear away from the edges of the storm and be absorbed into the surrounding cloud bands. Images from amateur and professional observers showed the spot looking ragged and partially disintegrated, prompting headlines about its imminent demise. NASA clarified that the spot was not actually breaking apart. The flakes were material being stretched out and absorbed at the edges, a normal part of the storm's interaction with the surrounding atmosphere. But the event underscored the degree to which the storm is visibly changing on observable timescales. Each passing year of Hubble Space Telescope monitoring shows a slightly smaller, slightly rounder storm than the year before. The trend is unambiguous. The rate of shrinkage has not been constant. There have been periods of faster and slower change, but the overall direction is clear. Why is it shrinking? The honest answer is that we do not fully know, and this is one of the genuine open questions in planetary science. Several mechanisms have been proposed. The storm may be losing energy to the surrounding atmosphere as its size decreases and its interaction with the surrounding jet streams changes. Smaller atmospheric vortices, vorticity in the surrounding atmosphere, may be gradually eroding the edges of the spot by interacting with it and stripping away material. The spot may be changing as the underlying atmospheric dynamics of Jupiter's southern hemisphere evolve on long timescales. What is clear from Juno spacecraft observations is that the Great Red Spot's roots extend deep into Jupiter's atmosphere, much deeper than scientists expected, reaching down to depths of at least 300 to 500 kilometers below the visible cloud tops. The storm is not a shallow surface feature. It is a deep, three-dimensional structure anchored in layers of Jupiter's atmosphere that we can barely probe. Its ultimate fate depends on dynamics we do not fully understand. The possibility that the Great Red Spot could disappear entirely, that the most recognizable feature of the solar system's largest planet could simply dissolve and be gone within decades, is not a catastrophe in any physical sense. Jupiter will not be damaged. Its atmosphere will redistribute the energy the storm currently organizes. But it is a reminder that even the features of solar system objects that seem permanent and definitional, the features that appear on every textbook illustration, on every poster, in every documentary, are not permanent. They are dynamical states maintained by ongoing physical processes, subject to change and eventual dissolution. The Great Red Spot has dominated Jupiter's appearance since before the United States was a nation. It may be gone before many of the people watching this video reach old age. There are also other storms on Jupiter, and they have their own complicated dynamics. The South Equatorial Belt, the brown band south of the equator where the Great Red Spot sits, periodically fades and revives in a process that appears to involve large-scale atmospheric reorganizations. In 2000, 3 smaller anticyclonic storms, called white ovals, merged into a single storm that astronomers named Oval BA, sometimes called Red Spot Jr., because it subsequently reddened in color, possibly as it grew and began sampling deeper atmospheric layers, mimicking some of the processes that color the Great Red Spot. The fact that Oval BA reddened in color after merging suggests that the reddening of storms may be a predictable consequence of their depth and energy, giving some clues about the chemical processes involved. Chapter 4: Jupiter has no surface. And what that actually means is stranger than you think. One of the things most people know about Jupiter is that it is a gas giant, a planet without a solid surface, where there is no ground to stand on. This is true. But the simplified version of this fact, it's just gas all the way down, misses something so profound and so strange that it changes the entire way you think about what Jupiter is. Jupiter is not gas all the way down. It transitions through several completely distinct states of matter as you descend through it, and the state of matter at Jupiter's depths is something that does not exist naturally anywhere on Earth, and that can only be produced in laboratories under extreme conditions for fractions of a second. Start at the top. Jupiter's outermost atmospheric layer, the ammonia ice cloud layer that gives the planet its banded appearance, is where we see the planet's visual surface from spacecraft and telescopes. This layer sits at pressures of roughly 0.5 to 1 times Earth's atmospheric pressure, temperatures here are approximately minus 145 degrees Celsius. The atmosphere is composed mostly of hydrogen and helium, with traces of water, methane, ammonia, and various organic molecules. Descend through the cloud layers. The ammonia ice clouds at the top, then a layer of ammonium hydrosulfide clouds deeper down, then water clouds deeper still. And the pressure and temperature both increase rapidly. By the time you reach about 50 kilometers below the visible cloud tops, you are already at pressures several times Earth's atmospheric pressure, and temperatures of several hundred degrees Celsius. The atmosphere becomes thicker and hotter as you go deeper. Continue descending. At some depth, roughly 10,000 to 20,000 kilometers below the cloud tops, at pressures of around 2 million times Earth's atmospheric pressure and temperatures of approximately 10,000 Kelvin, something remarkable happens to the hydrogen. Ordinary molecular hydrogen, H2, two hydrogen atoms bonded together, is the dominant component of Jupiter's outer atmosphere. But at these extreme pressures and temperatures, the molecules are compressed so tightly that the electrons can no longer be said to belong to any individual atom or molecule. The electrons become delocalized. They flow freely through the material, the way electrons flow through a metal. The hydrogen does not become a solid or a gas or an ordinary liquid. It becomes something called metallic hydrogen, a state of matter in which hydrogen behaves like a liquid metal, conducting electricity and heat with extraordinary efficiency. Metallic hydrogen is not hypothetical. It has been produced in laboratory experiments using diamond anvil cells, devices that can squeeze small samples of material to extreme pressures. And using shock compression experiments, where explosive shock waves momentarily compress hydrogen to the required pressures. But in laboratory conditions, metallic hydrogen has been maintained for only fractions of a second in samples of microscopic size. In Jupiter, metallic hydrogen exists in a layer that is tens of thousands of kilometers thick and has been there since the planet formed 4.5 billion years ago. In January 2017, a team of researchers at Harvard University, led by Ranga Dias and Isaac Silveira, announced that they had produced a tiny sample of solid metallic hydrogen, not just the liquid conducting phase, but an actual solid phase, at a pressure of approximately 495 gigapascals in a diamond anvil cell, briefly creating a material that had been theorized for over 80 years. The sample was small and unstable, and the result has been contested by other researchers who were unable to reproduce it. But the attempt illustrates the extraordinary effort that goes into understanding the physics of what fills Jupiter's interior. Experiments that strain the limits of laboratory technology to produce for fractions of a second what Jupiter has maintained for billions of years across a volume the size of several Earths. This metallic hydrogen layer is why Jupiter has one of the most powerful magnetic fields in the solar system, about 20,000 times stronger than Earth's magnetic field at the surface. Earth's magnetic field is generated by the convective motion of liquid iron in its outer core, a dynamo driven by the rotation of conducting fluid. Jupiter's magnetic field is generated by the convective motion of metallic hydrogen in its interior. The same physical principle, but with conducting liquid hydrogen instead of conducting liquid iron. The scale is enormous. Jupiter's magnetosphere, the region of space dominated by its magnetic field, extends up to 7 million kilometers toward the Sun and over 700 million kilometers in the opposite direction, forming a tail that stretches all the way to Saturn's orbit. Descend further past the metallic hydrogen layer toward Jupiter's center, and the density continues to increase. There is no solid liquid phase, boundary, no clear transition from liquid to solid, because at such extreme pressures, the concept of solid and liquid begins to blur. The material in Jupiter's deep interior is better described as a hot, dense, viscous fluid, in which the distinction between solid and liquid depends on the timescale on which you are asking the question. At the center, there is what most textbooks describe as a rocky core, a ball of rock and ice, perhaps 10 to 15 Earth masses, that formed first and then accreted the surrounding gas. But the Juno spacecraft, which has been orbiting Jupiter since 2016 and measuring its gravitational field with extraordinary precision, has upended this simple picture in a specific and fascinating way. The data from Juno suggests that Jupiter does not have a compact, well-defined rocky core. Instead, it appears to have a fuzzy core, a diffuse region in the center, where the rock and ice of the core material has dissolved and mixed into the surrounding metallic hydrogen, blurring the boundary between the dense central material and the outer layers. The fuzzy core may extend to about 30 to 50% of Jupiter's radius. A diffuse, partially mixed interior, rather than a clean ball of rock surrounded by layers of gas. This fuzzy core finding is one of the most significant results from Juno, because it challenges the standard model of how giant planets form, the core accretion model, which predicts a distinct, compact, rocky core at the center. If Jupiter's core is genuinely diffuse and partially dissolved, something must have disturbed it. One leading hypothesis is that Jupiter was struck by a massive protoplanet, possibly 10 Earth masses, very early in the solar system's history, perhaps 4.5 billion years ago, and the impact was energetic enough to dilute the core by mixing its rock and ice throughout a larger volume of the planet. This would also explain why Jupiter's interior is more mixed and heterogeneous than simple. Models predict. Chapter 5: Jupiter's moons are worlds unto themselves, and one of them has the biggest ocean in the solar system. Galileo discovered Jupiter's 4 largest moons in 1610. He called them the Medicean stars, an obsequious nod to his Florentine patrons. But history has given them his name: the Galilean moons, Io, Europa, Ganymede, and Callisto. The standard presentation of these moons, in textbooks, in documentaries, in popular science, tends to treat them as interesting but secondary characters, geological curiosities in the shadow of their enormous host planet. This is the wrong framing. Each of the Galilean moons is a world of extraordinary character, and taken together, they represent 4 of the most scientifically significant objects in the solar system. Let us go through them properly, because what they contain is not incidental to the story of Jupiter. It is central to the reason Jupiter matters for astrobiology, for planetary science, and for the future of solar system exploration. Io is the innermost of the 4 Galilean moons and the most geologically active world in the solar system, more volcanically active than Earth in terms of the total energy output of its volcanism. It has over 400 active volcanoes. Its surface is covered in sulfur and sulfur dioxide, deposits in shades of yellow. orange, red, and white, giving it an appearance sometimes compared to a pizza. Though this is a trivializing description of one of the most dynamic geological environments anywhere in the known universe. Its mountains are enormous, some exceeding 18 kilometers in height, taller than any mountain on Earth. And they are not volcanic mountains. They are tectonic mountains built by the compression of Io's crust. The source of Io's extraordinary volcanic activity is tidal heating. As Io orbits Jupiter, it is simultaneously pulled gravitationally by Jupiter, Europa, and Ganymede. The competing gravitational tugs from these different objects force Io's orbit to remain slightly elliptical rather than a perfect circle, which means Io's distance from Jupiter varies slightly as it orbits. This varying distance changes the strength of Jupiter's tidal pull on Io's interior, and the changing tidal distortion flexes and kneads Io's interior the way you might flex a rubber ball in your hands. The friction from this continuous flexing generates an enormous amount of heat, far more than can be accounted for by radioactive decay or any other internal source. Io is being literally squeezed into heat by the competing gravitational pulls of its neighbors. Io's surface is so geologically active that it has essentially no impact craters. They are erased by volcanic activity before they can accumulate. The surface you see today is not ancient. It is being continuously renewed on timescales of millions of years at most. And some regions are actively being resurfaced in human observation times. When Voyager 1 flew past Io in 1979, it captured images of active volcanic eruptions, plumes of material erupting hundreds of kilometers above the surface, the first time active volcanic eruptions had been observed on any world other than Earth. This was one of the most dramatic discoveries of the Voyager mission. Europa. Europa is the second Galilean moon and the most celebrated in astrobiology. It is approximately the size of Earth's moon, covered in a smooth shell of water ice that appears brilliantly white from space, crossed by dark reddish-brown lines that are fractures and surface features in the ice. Its surface is remarkably flat, the flattest large solid surface in the solar system. With virtually no topographic relief, more than a few hundred meters above the surrounding terrain, despite covering an area comparable to Earth's dry land. The reason for Europa's smooth surface is that beneath the ice shell, somewhere between 10 and 30 kilometers below the visible surface, is a liquid water ocean, a real global salty liquid water ocean, maintained in liquid state, not by solar energy. Europa receives relatively little, but by the same tidal heating that powers Io's volcanism, operating at a lower intensity on Europa's water ice shell. The ocean is estimated to contain somewhere between 2 and 3 times as much liquid water as all of Earth's oceans combined. It is the largest ocean in the solar system. The possibility that Europa's ocean harbors life is one of the most intensely discussed questions in modern astrobiology. The ingredients that life requires, liquid water, an energy source, and the chemical raw materials for biochemistry, appear to be present. The tidal heating provides energy. The ocean has been in contact with the rocky seafloor for billions of years. And hydrothermal vents, underwater volcanic systems where hot, chemically enriched water circulates through the rock and provides energy for chemosynthetic life, are thought to be possible or even likely. On Earth, deep-sea hydrothermal vent ecosystems support rich biological communities entirely independent of sunlight, deriving energy from chemical gradients between the hot vent fluid and the surrounding cold seawater. If similar systems exist on Europa, they could in principle support life. The evidence for the ocean comes from multiple sources. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, measured perturbations in Jupiter's magnetic field near Europa, consistent with an electrically conducting layer within Europa, most plausibly a salty liquid water ocean. The Hubble Space Telescope has observed what appear to be water vapor plumes erupting from Europa's surface. Though these plumes are smaller, less frequent, and less certain than those observed at Enceladus. The surface geology, the complex of fractures, ridges, and chaos terrain, regions where the ice shell appears to have broken, shifted, and refrozen, is most easily explained by an ocean that is occasionally in active contact with the surface, with tidal forces periodically disrupting the ice shell. NASA's Europa Clipper mission was launched in October 2024 and is en route to Jupiter, scheduled to arrive in 2030 and conduct approximately 50 close flybys of Europa over the course of its mission. It will measure the thickness and structure of the ice shell, characterize the ocean's chemistry through analysis of whatever materials are erupted or sublimated to the surface, and assess the potential habitability of the ocean. It will not land on Europa or drill through the ice. Those objectives are for potential future missions, but it will give us, for the first time, a comprehensive characterization of what Europa's ocean is actually like. Ganymede is the largest moon in the solar system, larger than the planet Mercury, with a diameter of approximately 5,268 kilometers compared to Mercury's 4,879 kilometers. This fact alone is remarkable. The solar system has a moon that is larger than a planet. Ganymede has a mass approximately twice that of the moon and a radius larger than Mercury, though its lower density, it contains large amounts of water ice, means its mass is less than Mercury's. Ganymede is the only moon in the solar system known to have its own internally generated magnetic field. Like Earth and Jupiter, it has a magnetosphere, a region of space dominated by its own magnetic field, rather than Jupiter's. This is produced by convective motions of liquid iron in Ganymede's outer core, making Ganymede geologically more similar to the terrestrial planets than to most other moons. Ganymede also appears to have a subsurface ocean of liquid water buried beneath an ice shell and above a layer of rock, with the evidence coming from Hubble Space Telescope observations of its aurora. The rocking of the aurora in response to Jupiter's magnetic field showed that an electrically conducting layer within Ganymede, most likely a salty ocean, was dampening the expected response to Jupiter's field. The European Space Agency's JUICE, Jupiter Icy Moons Explorer mission, launched in 2023, is designed in part to characterize Ganymede's ocean and its potential habitability when it arrives at Jupiter in 2031. Callisto is the outermost and most heavily cratered of the Galilean moons. Its surface is one of the most impact-cratered surfaces in the solar system, offering a record of bombardment extending back to the early solar system. Unlike the other three Galilean moons, Callisto shows no evidence of significant internal geological activity. No volcanism, No tectonic resurfacing, no signs of a differentiated interior with separate layers of rock and ice. It appears to be essentially primordial, a roughly homogeneous mixture of rock and ice that has changed little since the solar system's formation, making it a kind of frozen archive of early solar system conditions. Despite its apparently dead interior, Callisto may also have a subsurface ocean, again suggested by magnetic field perturbations measured by the Galileo spacecraft. If this is correct, Callisto has a liquid water ocean maintained not by tidal heating. Its orbit is too distant for significant tidal effects, but possibly by a small amount of residual radioactive heating and the antifreeze effect of dissolved salts lowering the freezing point of the water. A Callisto ocean, if it exists, would be less energetically active and less chemically dynamic than Europa's, and therefore a less likely habitat for life. But its existence would be scientifically significant in its own right. The 4 Galilean moons together represent a microcosm of solar system diversity. A volcanically active rocky world, an ice-covered ocean world with potential habitability, the largest moon with its own magnetic field, and a probable ocean, and a cratered primordial archive. They are not secondary characters. They are the main act of the Jupiter system for anything that cares about the possibility of life beyond Earth. Chapter 6. Jupiter's Formation. Story is nothing like what you were taught. Most people, if they remember anything from school about how the solar system formed, remember something like this. The solar nebula, a cloud of gas and dust, collapsed under gravity, the sun formed in the center, and the remaining material flattened into a disk from which the planets condensed. Rocky planets formed in the inner solar system because only rocks and metals could survive the heat near the young sun. Gas giants like Jupiter formed in the outer solar system where temperatures were cold enough for ices to condense, providing the solid material for a large core, which then accreted a massive gas envelope. This is the core accretion model, and it is the standard framework for planet formation. It is broadly correct as a general picture. But for Jupiter specifically, the actual formation story is dramatically different from this simple narrative. And the difference changes our understanding not just of Jupiter, but of the entire architecture of the solar system. The first revision concerns timing. The core accretion model predicts that forming Jupiter's core takes a significant amount of time, perhaps several million years, as small planetesimals collide and accumulate into progressively larger objects. But measurements of meteorites provide a different picture. Meteorites contain tiny grains of material that condensed directly from the solar nebula. And the isotopic compositions of these grains, particularly the ratios of certain isotopes of molybdenum, ruthenium, and other elements, can tell us about the chemical conditions in different parts of the early solar nebula. What these isotopic measurements reveal is extraordinary. The material in the outer solar system was chemically segregated from the material in the inner solar system very early, within the first million years after the sun formed. Something was acting as a barrier between the inner and outer solar system, preventing the mixing of material across the barrier. The most plausible candidate for this barrier is the early formation of Jupiter itself, or more precisely, the formation of Jupiter's core and the gap it carved in the protoplanetary disk. This means Jupiter's core formed within approximately 1 million years of the solar system's formation, making Jupiter not just the oldest planet, but possibly the first planet to form, establishing the basic architecture of the solar system before any of the other planets had taken shape. The implications of this early formation go beyond just Jupiter's history. If Jupiter established a barrier in the protoplanetary disk within the first million years, it fundamentally shaped the chemical and physical environment in which every other planet formed. The rocky planets of the inner solar system, including Earth, formed in a chemical environment that was separated from the outer solar system's volatile, rich material, partly because Jupiter was already there, acting as a dynamical wall. The volatile content of Earth, its water, its carbon, its nitrogen, is partly a function of what Jupiter allowed to pass through and what it deflected. Jupiter's early formation is therefore a precondition for the specific chemical composition of every other planet in the solar system, including the planet that eventually produced you. The second, more dramatic revision concerns where Jupiter formed and how it got to where it is today. In the standard picture, Jupiter formed roughly where it is now, in the outer solar system, at approximately 5 astronomical units from the Sun. But there is growing evidence that this is wrong, that Jupiter originally formed much farther from the Sun, and then migrated inward substantially before migrating back outward to roughly its current position. This is the Grand Tack hypothesis proposed by Kevin Walsh and colleagues in 2011. The Grand Tack scenario goes like this. Jupiter formed at approximately 3 to 3.5 astronomical units from the Sun, closer to where the asteroid belt is today. As Jupiter grew massive, it carved a gap in the protoplanetary disk, the rotating disk of gas and dust from which planets form. And the gravitational interaction between Jupiter and the disk caused Jupiter to migrate inward. Jupiter migrated inward to approximately 1.5 astronomical units, deep into the inner solar system, potentially sweeping through the region now occupied by Mars. This inward migration was the Grand Tack, like a sailing ship tacking into the wind. Then Saturn entered the picture. Saturn, forming in the outer solar system, grew massive enough to begin its own inward migration. Saturn migrated inward faster than Jupiter because it was smaller and coupled differently to the disk. When Saturn caught up to Jupiter and the two planets approached a 2 to 3 mean motion, resonance, a gravitational configuration where Saturn completes 2 orbits for every 3 completed by Jupiter, the combined gravitational effect changed the direction of migration for both planets. Instead of continuing inward, they both began to migrate outward. Jupiter tacked, reversed course, and moved outward to approximately its current position at 5.2 astronomical units. The Grand Tack hypothesis explains several otherwise puzzling features of the solar system. It explains why Mars is so small. Jupiter's inward migration swept material out of the region where Mars would have formed, depriving Mars of the raw material needed to grow to full planetary size. Without the Grand Tack, simulations suggest Mars should be about the same mass as Earth, but Mars is only about 1/10 of Earth's mass, a long-standing puzzle called the Small Mars problem. It explains the composition of the asteroid belt. The Grand Tack would have mixed inner solar system material, rocky metallite, with outer solar system material, carbonaceous, volatile rich, into the asteroid belt, during Jupiter's inward sweep, producing the compositionally diverse population of asteroids we actually observe. And it explains the relative scarcity of very large rocky planets in the inner solar system. Jupiter's passage depleted the inner solar system of the material that would have formed larger terrestrial planets. The grand tack hypothesis is not universally accepted. It is a theoretical model based on simulations, and alternative explanations for the same observations have been proposed. But it represents the current frontier of understanding for how Jupiter's formation and migration shaped the entire architecture of the solar system. And it is a fundamentally different picture from the gas giant formed in the outer solar system, and has been there ever since narrative of the simplified account. There is one further wrinkle in Jupiter's formation story that is worth mentioning: the NICE model, which describes a later dynamical instability in the solar system that may have scattered the giant planets into their current orbits. The NICE model, named for the French city of Nice, where it was developed, proposes that after the planets formed and the gas disk dissipated, the outer solar system underwent a period of gravitational instability triggered by Jupiter and Saturn crossing a mean motion resonance. This instability caused dramatic reshuffling of the outer planets' orbits and scattered enormous numbers of outer solar system objects into the inner solar system. An event that may correspond to the late heavy bombardment, the period of intense impact cratering recorded in the geology of the Moon and other inner solar system bodies. Under the NICE model, the orbital positions of Jupiter, Saturn, Uranus, and Neptune that we observe today are not where these planets originally formed. They were established by a chaotic gravitational rearrangement that occurred hundreds of millions of years after the solar system's formation, during which Uranus and Neptune were significantly displaced from their original positions. Jupiter's current position at 5.2 astronomical units is the outcome of multiple phases of migration and dynamical instability, not a simple reflection of where it formed. Chapter 7. Jupiter has rings, and almost nobody knows this. Here is a question that catches almost everyone off guard, even people who consider themselves reasonably well-informed about astronomy. Does Jupiter have rings? The instinctive answer for most people is no. Rings are Saturn's thing. Saturn is the ringed planet. Jupiter is the big planet with the storm. The association between Saturn and rings is so strong in popular culture that the idea of Jupiter having rings feels like a trick question. Surely, if Jupiter had rings, we would know about them. They would be in every documentary. Every textbook image would show them. Jupiter has rings. It has had rings since at least the early solar system. They just are not visible to the naked eye, or even to most telescopes pointed at Jupiter from Earth, because they are extraordinarily faint, thin, tenuous, made of tiny dark dust particles rather than the bright ice particles that make Saturn's rings visible from Earth with a small telescope. Jupiter's rings are dark where Saturn's rings are bright, because they are made of a fundamentally different material. Jupiter's rings are composed of microscopic dust grains knocked off the surfaces of Jupiter's small inner moons by micrometeorite impacts. When tiny space rocks hit the small moons, Metis, Adrastea, Amalthea, and Thebe, they launch dust particles into orbit around Jupiter, and these dust particles continuously replenish the ring system. The rings were discovered not by a careful ground-based observation, but effectively by a targeted gamble. When Voyager 1 flew past Jupiter in 1979, mission controllers targeted its camera at Jupiter's equatorial plane, looking edge-on the chance that rings might exist. A single long exposure photograph caught a faint, thin ring of light. The discovery was not a headline moment in the way that some spacecraft findings are. Jupiter's rings are so faint and so thin that the discovery photo barely registers as interesting at first glance. But it fundamentally changed the picture of which planets have rings. Saturn's rings had been known since the 17th century. Uranus's rings were discovered in 1977 when Uranus occulted a star, and the star's light dimmed at symmetrical distances on either side of the planet, revealing ring material. Jupiter's rings, discovered in 1979, and Neptune's rings, discovered in 1984 through a similar stellar occultation method, completed the picture. Every planet in the outer solar system has a ring system of some kind. The notion that rings are Saturn's exclusive feature is simply wrong. It is worth pausing on this point specifically because it illustrates something important about how popular astronomy works. Saturn's rings are extraordinarily beautiful and visible. You can see them with a cheap telescope. Jupiter's rings require a spacecraft with carefully targeted cameras. The result is that Saturn's rings are famous and Jupiter's rings are unknown to most people. Not because Saturn's rings are more scientifically significant, but because they are prettier and easier to see. The lesson extends beyond rings. The parts of the solar system that are well known to the general public are disproportionately the parts that are visually spectacular or easy to observe. The parts that are harder to see, faint rings, subsurface oceans, metallic hydrogen interiors, diffuse fuzzy cores, are where much of the actual science currently lives. The visible surface of things is not where the interesting questions are. The interesting questions are always found deeper in. Jupiter's ring system consists of 4 components. The innermost is the halo ring, a thick, faint torus of material extending from about 92,000 kilometers to about 122,500 kilometers from Jupiter's center. Outside, this is the main ring, thinner and brighter than the halo, though still extraordinarily faint by any human standard. At approximately 122,500 to 129,000 kilometers from Jupiter's center. Beyond the main ring are the 2 gossamer rings, named for their extreme tenuousness, one associated with the moon Amalthea and one with the moon Thebe. The gossamer rings extend outward to roughly the orbital radii of their respective source moons. The Galileo spacecraft's observations of the ring system confirmed the dust from moon's origin story. When Galileo observed the rings in forward scatter geometry, looking back towards the sun with the rings between the spacecraft and the sun, the rings appeared dramatically brighter. This is characteristic of forward scattering by very small particles. Tiny dust grains scatter sunlight most efficiently in the forward direction, which is why the rings are essentially invisible from Earth, where we always observe Jupiter with the sun roughly behind us in backscatter geometry, but become apparent when observed from positions that allow forward scatter. This same geometry, visible only from within or beyond the ring system, looking back towards the sun, explains why Jupiter's rings eluded discovery until a spacecraft was actually there. What the rings tell us about Jupiter's immediate environment is also interesting. The fact that the rings are continuously replenished by dust from micrometeorite impacts on small inner moons means that they are dynamic. They are not ancient remnants of Jupiter's formation, but actively maintained structures in a constant state of supply and loss. Dust particles in the main ring have lifetimes of perhaps a few thousand years before they spiral inward due to drag forces from Jupiter's magnetosphere, which carries ionized gas that exerts a small but cumulative drag on charged dust particles. The rings we see today are not the rings that existed 1 million years ago, and will not be the rings that exist 1 million years hence. They are a transient phenomenon, maintained in approximate steady state by the ongoing supply from the small inner moons. Chapter 8, Jupiter's magnetic field, is one of the most violent environments in the solar system. Jupiter's magnetic field is not merely strong. It is the generator of one of the most energetically violent environments in the solar system outside the Sun itself. A region of space that would kill an unprotected human being in minutes, that generates radio emissions powerful enough to be detected from Earth with a simple radio antenna, and that drives a continuous electrical current between Jupiter and its moon, Io, that would dwarf the output of every power plant on Earth combined. Jupiter's magnetic field at its cloud-top surface is approximately 4.2 Gauss on average, about 20,000 times stronger than Earth's surface magnetic field of approximately 0.5 Gauss. But the magnetosphere extends far beyond the planet itself. Jupiter's magnetosphere, the region of space dominated by Jupiter's magnetic field rather than the solar wind, extends approximately 3 to 7 million kilometers toward the Sun and stretches more than 700 million kilometers in the anti-sunward direction, forming a vast magnetotail that extends roughly to Saturn's orbital distance. Jupiter's magnetosphere is the largest structure in the solar system outside the Sun's own heliosphere. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear in the sky several times larger than the full moon. Within this magnetosphere, charged particles, electrons and ions, are trapped and accelerated to extreme energies. Jupiter's radiation belts, the analog of Earth's Van Allen belts, are trapped zones of energetic particles surrounding the planet. Earth's Van Allen belts are intense enough to pose a radiation hazard to satellites and astronauts. Jupiter's radiation belts are in an entirely different category. A spacecraft flying through Jupiter's inner radiation belt without shielding would receive a lethal radiation dose in seconds. The radiation environment near Io, which orbits deep within Jupiter's intense inner magnetosphere, is so intense that early mission planning for spacecraft visiting the Jovian system had to account for cumulative radiation damage to electronics. The Galileo spacecraft, which orbited Jupiter for 8 years from 1995 to 2003, suffered progressive radiation damage that eventually degraded its instruments and subsystems. Its mission was terminated in 2003 by deliberately plunging it into Jupiter's atmosphere to avoid the possibility of it contaminating Europa with Earth microbes should it eventually crash there. Juno, the current Jupiter orbiter, operational since 2016, follows a highly elliptical polar orbit specifically designed to minimize its exposure to the radiation belts. Its orbit carries it in close to Jupiter at each periove, closest approach, but spends most of its time far from the planet, and its trajectory takes it over Jupiter's poles rather than through the equatorial plane, where the radiation belts are most intense. Even with this careful design, Juno has accumulated significant radiation damage, and its instruments and systems have been affected by the Jovian radiation environment over the course of its extended mission. The interaction between Jupiter's magnetic field and Io is one of the most extraordinary phenomena in the solar system, and it is almost never discussed in popular accounts of Jupiter. Io orbits within Jupiter's magnetosphere and, because of its volcanic activity, continuously pumps material into space around it. Io's volcanoes release approximately 1 ton per second of material, mostly sulfur dioxide and sulfur compounds, into Io's local environment. This material gets ionized, stripped of electrons, by UV radiation and trapped in Jupiter's magnetic field, forming a donut-shaped region of plasma called the Io plasma torus, a ring of ionized sulfur and oxygen surrounding Jupiter at roughly Io's orbital distance. The interaction between the moving Io plasma torus and Jupiter's rotating magnetic field generates a powerful electrical circuit called the Io flux tube. Jupiter's magnetic field rotates with the planet at Jupiter's rotational period of approximately 10 hours. Io orbits Jupiter at a different rate, taking about 42 hours to complete one orbit. This difference in rotation rate between the magnetic field and Io's orbital motion drives an enormous electrical current between Io and Jupiter along magnetic field lines. A current estimated at approximately 5 million amperes, with a power output of roughly 2 trillion watts. For comparison, the total global electricity generation capacity of Earth is approximately 8 trillion watts, so the Io flux tube delivers roughly 1/4 of Earth's total power generation capacity as a continuous electrical current flowing between a moon and a planet. This current heats the upper atmosphere of Jupiter at the locations where the flux tube intersects the planet, creating bright ultraviolet auroral spots. The Io footprint aurora, directly visible in Hubble Space Telescope. Ultraviolet images as bright spots on Jupiter's polar regions. Jupiter also produces natural radio emissions, decametric radio bursts, that are powerful enough to be detected with a basic radio receiver on Earth. These emissions are generated by electrons spiraling along Jupiter's magnetic field lines and producing coherent radio emission through a mechanism related to the electron-cyclotron Maser instability. Radio astronomers on Earth can listen to Jupiter. The radio bursts sound like rushing water or crackling static, with a characteristic swooshing quality that amateur radio operators have been recording since the 1950s. This makes Jupiter the only object in the solar system outside the Sun that is routinely monitored by amateur radio astronomers with relatively simple equipment. The fact that a planet's magnetic field activity is detectable from 800 million kilometers away, using equipment you can build in a garage, is a striking illustration of the scale of Jovian magnetic phenomena. Jupiter's auroras are also extraordinary by terrestrial standards. On Earth, the aurora borealis and aurora australis are caused by energetic particles from the solar wind entering the atmosphere along magnetic field lines near the poles. Jupiter's auroras are far more powerful. They are the most energetic auroras in the solar system. And they are driven not primarily by the solar wind, but by Jupiter's own rotation and the Io plasma torus. The continuous supply of material from Io's volcanism ionized into the plasma, torus, and then drawn into Jupiter's magnetic field, sustains a permanent, powerful auroral display at Jupiter's poles that is visible in ultraviolet images from the Hubble Space Telescope. The auroras are not occasional or seasonal. They are continuous, sustained, and enormously powerful, radiating more energy per second than all of Earth's weather systems combined. Hubble's ultraviolet images of Jupiter's poles show permanent auroral ovals, hundreds of thousands of kilometers wide, flickering with the Io footprint aurora spots as Io's flux tube sweeps around the planet with every Jovian rotation. In the ultraviolet, Jupiter's poles are the most energetic places in the solar system outside the Sun's corona. Chapter 9. What Juno Taught Us. The Interior. We got completely wrong. The Juno spacecraft arrived at Jupiter on July 4th, 2016, after a 5-year journey from Earth. It was the first spacecraft specifically designed to study Jupiter's interior, atmosphere, and magnetic field. From a polar orbit, previous Jupiter orbiters, Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Ulysses, Cassini during its flyby, and Galileo, had all flown in or near Jupiter's equatorial plane, limiting their ability to study the planet's poles and measure its gravity field with the precision needed to constrain interior models. Juno's primary science objectives were to determine Jupiter's water content, which constrains models of how the planet formed, map Jupiter's gravitational and magnetic fields with unprecedented precision, and study the atmosphere below the visible cloud tops. What Juno found challenged essentially every model of Jupiter's interior that existed before its arrival. Water content, a fundamental surprise. One of the central predictions of Jupiter's formation models concerns the abundance of water in Jupiter's deep atmosphere. Water in a giant planet comes primarily from oxygen that was incorporated into the planet during formation. The ratio of oxygen to hydrogen in Jupiter's atmosphere, expressed as a ratio relative to the solar abundance, constrains models of where and how Jupiter formed. If Jupiter formed in the cold outer solar system where water ice could condense and be incorporated into the growing planet, its oxygen, and hence water, content should be higher than the solar value. If it formed closer to the Sun, it might have a different enrichment pattern. The Galileo probe, which descended into Jupiter's atmosphere in 1995, measured unexpectedly low water abundance, much lower than models predicted. For years, this was a puzzle. Juno resolved it. The Galileo probe entered Jupiter's atmosphere above an unusually dry region called a hot spot, a region of descending, dry atmospheric air that is not representative of the global average. Juno's microwave radiometer can measure water abundance across the entire globe at multiple locations, and the results show that Jupiter's average deep water abundance is consistent, with models and substantially higher than the Galileo probe measured. The deep atmosphere of Jupiter, globally, is enriched in water at approximately 2 to 5 times the solar value, consistent with Jupiter having accreted ice-rich material from the outer solar system. The Galileo probe had been sampling an outlier, and astronomers had spent 20 years puzzling over a measurement that turned out to be unrepresentative. The winds go much deeper than anyone thought. Jupiter's visible atmosphere shows a pattern of alternating east-west jets, the dark bands, belts, and bright zones that give Jupiter its striped appearance. Before Juno, a central open question was how deep these jet streams extend. Are they shallow, confined to the uppermost cloud layers like a thin weather system on Earth? Or do they extend deep into the interior? Juno's gravity measurements, measuring tiny variations in Jupiter's gravitational field as Juno flew by, provide the answer. The jet streams extend to a depth of approximately 3,000 kilometers below the cloud tops, roughly 5% of Jupiter's radius. Below 3,000 kilometers, the jet stream pattern disappears, presumably because the electrical conductivity of the deep atmosphere becomes high enough that Jupiter's magnetic field damps out the differential rotation. Above this transition depth, the atmosphere moves in the jet stream pattern. Below it, the deep interior rotates more nearly as a solid body. This 3,000-kilometer depth is striking for several reasons. First, it implies that the mass of atmosphere participating in the jet stream circulation is enormous, not a thin surface layer, but a substantial fraction of Jupiter's outer envelope. Second, it means that the beautiful banded structure we see from Earth is not a surface decoration. It is a deep, three-dimensional feature of Jupiter's atmospheric dynamics, penetrating thousands of kilometers into the planet. The bands are not painted on. They are carved in. The magnetic field is lopsided, and nobody expected that. Before Juno, Jupiter's magnetic field was assumed to be roughly dipolar, like Earth's, with a north magnetic pole, a south magnetic pole, and a relatively smooth field structure between them. This is what the limited pre-Juno measurements suggested. Juno's comprehensive polar orbit mapping of the magnetic field revealed something completely different. Jupiter's magnetic field is not symmetric. The northern hemisphere's magnetic field is dominated by a large patch of intense magnetic flux near the equator, while the southern hemisphere's field is more complex with multiple smaller patches and stronger small-scale features. The field is also stronger in the northern hemisphere than the southern hemisphere, and there is a prominent great blue spot, a region of intense outward magnetic flux in Jupiter's northern equatorial region, with no symmetrical counterpart in the south. This asymmetric, complex, patchy magnetic field suggests that Jupiter's magnetic dynamo, the convective metallic hydrogen layer generating the field, does not work like Earth's in any simple way. The mechanisms that produce the complex asymmetric field are not fully understood. Models of Jupiter's interior are now being substantially revised to account for the Juno magnetic field observations, and the dynamics of metallic hydrogen convection remain an active area of theoretical research. Polar cyclones, a discovery nobody predicted. When Juno first flew over Jupiter's poles, it imaged something that no previous spacecraft had ever seen, and that no model had predicted: enormous cyclonic storms clustered at the poles. At Jupiter's North Pole, Juno found a central cyclone surrounded by 8 circumpolar cyclones, arranged in a roughly octagonal pattern. At the South Pole, a central cyclone is surrounded by 5 circumpolar cyclones in a pentagonal arrangement. These polar cyclones are each comparable in size to the continental United States, thousands of kilometers across and have persisted throughout Juno's mission, maintaining their distinctive geometric configurations for years. They are not random chaotic eddies. They are stable, organized structures in a geometric arrangement that has survived for multiple years of observation. Why the polar cyclones maintain their geometric arrangement is an open question. On Earth, polar vortices are unstable. They break down and reform on seasonal timescales. Jupiter's polar cyclones appear to be in a dynamically stable configuration, which implies some mechanism for maintaining the geometric spacing against the tendency for storms to merge or scatter. This is not currently understood, and the Juno polar cyclone observations represent one of the most exciting genuine mysteries in planetary science. What makes the polar cyclone geometry particularly puzzling is the asymmetry between the North and South poles. The North Pole has 8 circumpolar cyclones arranged in an octagonal pattern. The South Pole has 5 circumpolar cyclones in a pentagonal pattern. If the dynamics were simply a reflection of Jupiter's rotation and basic atmospheric physics, you might expect the same geometry at both poles. The fact that the North and South poles have different numbers of cyclones suggests that something else, perhaps the asymmetry in Jupiter's magnetic field, perhaps latitudinal variations in the heat flux from the interior, perhaps some dynamical instability that can settle into different stable states, is determining the geometry independently at each pole. Understanding why the North has 8 cyclones and the South has 5 is not a minor technical question. It goes to the heart of how large planetary atmospheres organize themselves in the presence of rapid rotation and deep convection, dynamics that are relevant not just to Jupiter, but to every other giant planet in the solar system and to the hundreds of giant planets discovered in other star systems. Chapter 10: Jupiter and the Origin of Life on Earth. A connection nobody taught you. We have already discussed how Jupiter shaped the solar system's architecture through its formation, migration, and gravitational influence. But there is a more direct, more intimate connection between Jupiter and the origin of life on Earth that is rarely discussed in popular accounts of either Jupiter or the origins of life. Water is essential for life as we know it. Earth's surface is approximately 71% covered by liquid water. The total amount of water in Earth's oceans, ice sheets, atmosphere, and crust is enormous. About 1.4 billion cubic kilometers of water on the surface alone, with potentially as much or more locked in the mantle. Where did all this water come from? The Earth formed in the inner solar system, in the region close enough to the Sun that temperatures in the protoplanetary disk were above the water-ice sublimation point. The primordial Earth accreted from rocky, dry material. Planetesimals that formed inside the snow line, the distance from the Sun beyond which water ice could condense. In the standard model, Earth should have accreted with very little water, because the raw material it was built from was dry rock and metal. And yet, Earth is a water world. The discrepancy requires an explanation. The current consensus is that most of Earth's water was delivered by impacts after the initial planet formation, primarily by carbonaceous chondrite asteroids, which are a class of asteroids with high water content, up to 10 to 20% water by mass, bound in hydrated minerals. These water-rich asteroids originated in the outer asteroid belt or beyond, in regions where temperatures were low enough for hydrated minerals to form. The delivery of these water-rich asteroids to Earth-crossing orbits is not a random process. It was facilitated by the gravitational perturbations of Jupiter. Here is where the connection becomes specific. The grand tack, described in Chapter 6, involved Jupiter sweeping inward through the asteroid belt and then retreating. This migration did not just clear the asteroid belt, it mixed outer carbonaceous material into the inner belt, placing water-rich material in orbits that could subsequently be perturbed into Earth-crossing trajectories. The water that makes Earth habitable, the water that fills the oceans in which life originated, the water that is the solvent for all known biochemistry, got to Earth partly because Jupiter migrated and mixed the ingredients. There is a further connection in the late heavy bombardment, the period of intense impact activity that struck the inner solar system approximately 4 billion years ago. This bombardment, which is recorded in the heavily cratered highland regions of the Moon, and may have simultaneously delivered water and organic molecules to Earth while also heating the early oceans, was likely triggered by Jupiter and Saturn crossing a gravitational resonance that destabilized the outer solar system, the scenario described by the NICE model. If this is correct, then the chemical environment in which life originated on Earth, the soup of water, organic molecules, minerals, and energy sources that was present in the early ocean, was partly shaped by the dynamics of Jupiter's migration and the gravitational instability it helped trigger. Jupiter also has a direct connection to the organic chemistry relevant to life's origins. The carbonaceous chondrite asteroids that delivered water to Earth are also rich in organic molecules. Amino acids, nucleobases, sugars, and other prebiotic compounds have been identified in meteorites of this class. The Murchison meteorite, a carbonaceous chondrite that fell in Australia in 1969, contains over 90 different amino acids, most of which do not occur naturally on Earth, implying an extraterrestrial origin. These organic molecules were present in the carbonaceous material that the grand tack mixed into the inner solar system, the organic chemistry that seeded Earth's early ocean, possibly providing the raw materials from which life assembled itself, came in part from the same reservoir of outer solar system material that Jupiter's migration redirected toward the inner planets. This is not a speculation or a fringe hypothesis. It is a mainstream view in planetary science, supported by the isotopic compositions of Earth's water, which match outer belt carbonaceous chondrites better than inner belt material, by the organic contents of the relevant meteorite classes, and by the orbital dynamics that connect Jupiter's history to the delivery of this material. The version of Jupiter that most people know, the big planet with the storm sitting at 5 astronomical units, minding its own business, is a static snapshot of a planet whose history is dynamically entangled with the origin of every living thing on Earth. Chapter 11, Jupiter's atmosphere, has weather more complex than anything on Earth. We have discussed the Great Red Spot and the banded jet stream structure visible from Earth. But Jupiter's atmosphere is vastly more complex than these iconic features suggest, and the complexity extends to processes and phenomena that have no equivalent on Earth. Jupiter's bands, the alternating dark belts and bright zones that circle the planet in east-west stripes, are driven by a combination of Jupiter's rapid rotation, A Jovian day lasts only about 9 hours and 55 minutes, making it the fastest rotating planet in the solar system, and the convective heat rising from the interior. The dark belts are regions of descending air, dry, cloudless zones where the atmosphere is relatively clear at depth. The bright zones are regions of rising air, cloudy, moist regions where updrafts carry condensates, ammonia ice, ammonium hydrosulfide, water, to high altitudes where they form the white clouds that appear bright from above. The alternation of belts and zones is maintained by the east-west jet streams at their boundaries, which are themselves driven by the Coriolis effect from Jupiter's rapid rotation. This banded structure is more stable than any weather pattern on Earth, where the same Coriolis effect produces jet streams and weather systems that vary on timescales of days to seasons. Jupiter's jet streams are stable on timescales of years to decades. The North Equatorial Belt and South Equatorial Belt have been present and roughly consistent in width and position for as long as telescopic observations have been made. The rapid rotation and the depth of the jet streams, reaching 3,000 kilometers down, as Juno established, contribute to their stability. These are not fragile surface features, but deep-rooted, massive atmospheric structures that require enormous perturbations to disrupt. Yet disruptions do happen. The South Equatorial Belt, the dark band that borders the Great Red Spot to the north, periodically fades to near invisibility in events called South Equatorial Belt revival cycles. In these events, the dark belt whitens and almost disappears over a period of months, then dramatically and suddenly revives, usually with a dramatic outbreak of turbulent activity at a specific longitude that then spreads rapidly around the planet, restoring the belt to its normal dark appearance within weeks. These revival events happen every few years and have been observed for over a century. Despite their regularity, the precise mechanism of South Equatorial Belt fading and revival is not fully understood. The leading hypothesis involves changes in the ammonia cloud structure. Specifically, the belt fading when a thick layer of white ammonia, cirrus clouds, covers the normally dark belt region, and reviving when a localized disturbance breaks through the cirrus layer and triggers rapid global clearing. But the trigger for the initial whitening and the dynamics of the revival remain areas of active research. Jupiter also has lightning, and not like Earth's lightning. On Earth, lightning results from the separation of electric charge in water ice and water droplet clouds. Jupiter's lightning is thought to occur in its water cloud layer deep below the ammonia cloud tops, at pressures of several times Earth's atmospheric pressure and temperatures of a few hundred degrees Celsius. The Juno spacecraft has detected Jupiter's lightning in multiple ways. Through radio waves, the characteristic Whistler radio signals produced when lightning-generated radio emission travels along magnetic field lines. Through direct optical observations of lightning flashes seen on Jupiter's night side, and through energetic particle measurements. Jupiter's lightning is more powerful than Earth's. Individual discharges appear to release more energy than typical terrestrial lightning strokes, but it occurs at different frequencies in the radio spectrum. Earth's lightning produces a characteristic radio emission called spheric, at frequencies from a few kilohertz to a few megahertz. Jupiter's lightning produces emission primarily at a few megahertz, different enough in character that early radio searches for Jovian lightning missed it before the right frequency range was monitored. One feature of Jupiter's atmosphere that has received increasing attention is the presence of ammonia crystals raining downward from the upper atmosphere. Jupiter's visible cloud tops are made largely of ammonia ice crystals, and computer models suggest that in the belts, the descending regions, ammonia can condense and fall as ammonia hail or mush balls, aggregates of ammonia water ice that form when ammonia-rich air descends and encounters water ice crystals deeper in the atmosphere. These mush balls have been proposed as a mechanism for transporting ammonia from the upper atmosphere to deeper layers, and they may explain observed vertical variations in ammonia abundance that would otherwise be difficult to account for. Juno's microwave radiometer has detected variations in ammonia concentration that appear consistent with the mushball mechanism, making this one of the more intriguing recent developments in Jovian atmospheric science. Jupiter's atmospheric dynamics, the interplay of rotation, convection, jet streams, storms, lightning, and precipitation, represent a planetary-scale laboratory for fluid dynamics at parameters that Earth's atmosphere never achieves. The rapid rotation, the depth of the atmosphere, the absence of a solid surface to anchor weather systems, the enormous energy input from the interior, all of these produce atmospheric phenomena that challenge and extend our understanding of fluid dynamics and atmospheric physics in ways that directly inform our understanding of extrasolar giant planets, of which thousands have now been discovered. The absence of a solid surface deserves specific emphasis here because it changes the nature of atmospheric dynamics in ways that are not immediately obvious. On Earth, weather systems interact with the surface. Friction between moving air and the surface dissipates energy and slows winds. Mountains deflect airflows. Land-ocean temperature contrasts drive weather patterns. The surface is a boundary condition that shapes everything above it. Jupiter has no such boundary. The atmosphere transitions continuously from gas to liquid, to metallic liquid, to the diffuse core material, with no solid surface anywhere. Jupiter's weather system is not overlying a solid planet. It is the planet, at least in the sense of what we can observe and interact with. Storms on Jupiter do not dissipate against a surface. They dissipate against each other through merging, shearing, and energy transfer to the surrounding jet streams. This is why Jovian storms can survive for centuries. They are not scrubbing against terrain that dissipates their energy. They are free to persist as long as the temperature gradients and rotation that maintain them remain in place. The Great Red Spot's longevity is not mysterious. It is the expected behavior of a large energetic vortex in an atmosphere without a dissipating surface boundary layer. What is surprising is not that it has lasted so long, but that it is finally, after centuries, beginning to weaken. Chapter 12: Jupiter's True Scale, the numbers that still break your brain. We have been discussing Jupiter's properties and history throughout this video, but we have not yet simply sat with the raw scale of Jupiter and let the numbers do their work. Because even in a video full of corrections to the simplified Jupiter narrative, the scale of the planet itself, the basic physical dimensions, is genuinely staggering in ways that the largest planet description fails to communicate. Jupiter's equatorial radius is 71,492 kilometers. Earth's equatorial radius is 6,371 kilometers. The ratio is approximately 11.2. Jupiter's radius is 11.2 times Earth's, but volume scales as the cube of radius. 11.2 cubed is approximately 1,321. So Jupiter's volume is approximately 1,321 times Earth's volume. You can fit 1,321 Earths inside Jupiter. Not 10, not 100, but 1,321 spheres the size of Earth, packed inside Jupiter's volume. The popular claim that all the other planets could fit inside Jupiter is actually slightly understated. All 7 other planets combined have a total volume of about 870 Earths, which is less than Jupiter's volume of 1,321 Earths. You could fit all the other planets inside Jupiter with about 450 Earths worth of space left over. Jupiter's mass is 317.8 times Earth's mass. This is less than the volume ratio, 1,321 times, because Jupiter is less dense than Earth. It is largely composed of hydrogen and helium rather than rock and iron, giving it a mean density of about 1.33 grams per cubic centimeter compared to Earth's 5.51 grams per cubic centimeter. Jupiter is actually less dense than some water ice bodies in the outer solar system in terms of average density, though it is far more massive. The combination of enormous volume and modest density produces the 318 Earth mass figure. Jupiter's equatorial circumference is approximately 449,197 kilometers. The circumference of Earth at the equator is approximately 40,075 kilometers. Jupiter's circumference is therefore about 11.2 times Earth's, or about 449,000 kilometers, which is nearly the distance from Earth to the Moon, 384,400 kilometers. If you could drive around Jupiter's equator at highway speed without stopping, it would take you approximately 1,870 days, over 5 years of continuous driving. Jupiter's rotation rate, one full rotation every 9 hours 55 minutes, combined with its enormous size, means that the equatorial surface moves at an extraordinary speed relative to the rotation axis. Jupiter's equatorial circumference of 449,000 kilometers divided by the 9.92-hour rotation period gives an equatorial rotation speed of approximately 45,300 kilometers per hour, about 12.6 kilometers per second, or roughly 40 times faster than Earth's equatorial rotation speed. This extreme rotation rate is directly responsible for Jupiter's distinctive oblate shape. It is noticeably flattened at the poles, with an equatorial radius 7% larger than its polar radius, the most oblate of any planet in the solar system. The same rapid rotation drives the Coriolis effect that organizes Jupiter's atmospheric dynamics into its banded structure and maintains the stability of the jet streams. Jupiter's appearance, the bands, the zones, the stable storm systems, is fundamentally a consequence of how fast it spins. Jupiter's gravitational field at its cloud tops produces a surface gravity of approximately 24.79 meters per second squared, compared to Earth's 9.81 meters per second squared. At Jupiter's cloud tops, gravity is 2.53 times stronger than at Earth's surface. A person weighing 70 kilograms on Earth would weigh approximately 100 to 77 kilograms at Jupiter's cloud top level. This strong gravity is part of what makes the entire question of Jupiter's interior structure so exotic. The pressures generated by this gravitational field acting on Jupiter's enormous mass are what produce the metallic hydrogen layer, the fuzzy core, and the extreme physical states we discussed earlier. Jupiter's great red spot, even in its current shrunken state, at approximately 14,000 to 15,000 kilometers across, is larger than Earth. The entire continent of Africa is approximately 8,000 kilometers from north to south. The Great Red Spot, a storm, is nearly twice the north-south extent of the largest continent on Earth. At its historical maximum size of approximately 40,000 kilometers across, the Great Red Spot was over 3 times wider than Earth's diameter. A storm 3 Earths wide, on a planet 11 Earths across. Jupiter's moons are similarly scaled at the extreme of what the solar system offers. Ganymede, the largest moon, has a diameter of 5,268 kilometers, larger than Mercury's 4,879 kilometers. If Ganymede orbited the Sun instead of Jupiter, it would be classified as a planet. The fact that it is a moon captured in Jupiter's gravitational system is partly a consequence of how massive and dominant Jupiter is in the outer solar system. The Galilean moons are so large not just because of their own geology and history, but because Jupiter's enormous gravity and tidal influence shaped their evolution, and in the case of the outer moons, partly reflects the sheer scale of the zone of Jupiter's gravitational dominance. Chapter 13: What future missions will reveal? The questions we still cannot answer, despite everything Juno has revealed, and despite the coming Europa Clipper and JUICE missions. Jupiter retains fundamental mysteries that will require future spacecraft and future generations of scientists to resolve. The picture we have drawn in this video, the fuzzy core, the metallic hydrogen interior, the polar cyclones, the deep jet streams, the complex asymmetric magnetic field, is a picture full of open questions where it is not full of wrong answers. The corrections to the popular myths are real and important, but the corrected picture is itself incomplete, and acknowledging that incompleteness is part of what it means to take the science seriously. The nature of Jupiter's deep interior remains the most profound open question. The fuzzy core hypothesis, that Jupiter's core is a dilute, partially dissolved region rather than a compact ball of rock, needs to be tested with better measurements. Juno's gravitational measurements that first suggested the fuzzy core were extraordinary for their precision, but they are still measuring the integrated gravitational effect of the entire interior, not directly imaging what is inside. Future missions, with even more precise gravity measurements, or with seismological instruments capable of detecting Jovian oscillations, the giant planet equivalent of helioseismology, which uses sound waves propagating through the Sun's interior to image its structure, could provide much stronger constraints on the core's structure and composition. The origin of the fuzzy core is equally uncertain. The giant impact hypothesis, a protoplanet of approximately 10 Earth masses, struck Jupiter early in the solar system's history, diluting the core, is physically plausible and consistent with the fuzzy core data, but it is not the only explanation. Alternatively, the core may have been diluted by chemical erosion. Heavy elements dissolving out of the core and mixing upward into the surrounding metallic hydrogen layer over billions of years. Distinguishing between these scenarios requires understanding the solubility of rock and ice in metallic hydrogen at Jupiter's interior conditions, which requires laboratory experiments at pressures and temperatures that are extraordinarily difficult to achieve. The polar cyclones are one of the most visually spectacular and scientifically puzzling of Juno's discoveries. The mechanism by which these enormous cyclones maintain their stable geometric configurations, the octagonal arrangement at the North Pole, the pentagonal arrangement at the South Pole, is not understood. Why do the northern and southern poles have different numbers of cyclones? Why do the cyclones not merge, as Jupiter's smaller storms frequently do? What determines the spacing between the circumpolar cyclones? These questions go to the heart of atmospheric fluid dynamics at planetary scales and do not yet have satisfying answers. The origin and dynamics of Jupiter's magnetospheric activity, particularly the mechanisms that produce the extremely patchy asymmetric magnetic field revealed by Juno, require a substantially improved understanding of metallic hydrogen convection. The magnetic field of a planet is a direct window into the dynamics of its deep interior. Jupiter's complex lopsided field tells us that the convective motions in the metallic hydrogen layer are complex and non-uniform in ways that simple models did not anticipate. Understanding these dynamics requires both better observational data and better theoretical models of magnetohydrodynamics in metallic hydrogen, a field that is advancing but not yet at the point where Jupiter's field can be quantitatively explained. Europa Clipper, arriving at Jupiter in 2030, will address a different class of questions: the structure and composition of Europa's ocean and ice shell. Key questions include the thickness of the ice shell, which matters enormously for the possibility of any future lander or drilling mission. The chemistry of the ocean, particularly its pH, salinity, and redox state, which determine whether it is habitable. The nature and source of the reddish-brown surface material in Europa's chaos terrain, which may be material from the ocean brought to the surface, providing a chemical fingerprint of ocean chemistry accessible from orbit. And whether the Hubble-detected water vapor plumes are real and recurring. If the plumes are real and originating from the ocean, they represent an extraordinary opportunity, a natural sample return of ocean water to near-surface altitudes where a future spacecraft could collect and analyze it without drilling through kilometers of ice. The JUICE mission, primarily targeting Ganymede, will characterize Ganymede's ocean and magnetic field in detail for the first time, and will also conduct multiple flybys of Europa and Callisto. Together, JUICE and Europa Clipper will give us, for the first time, a comprehensive characterization of the three potentially ocean-bearing Galilean moons, answering questions about their habitability and providing the detailed reconnaissance needed to plan any future landed or subsurface missions. What no planned mission will fully answer is the question that motivates all of it. Is there life in Europa's ocean? That question requires a different class of mission, one that can reach the ocean directly, whether by drilling through the ice or reaching it at a plume. And such a mission is a generation away at minimum, dependent on the results of Europa Clipper and on the development of technologies for ice penetration and ocean access that do not yet exist in flight-ready form. The question of European life is a genuine scientific open question in the most important sense. It cannot be answered with current tools, and its answer, in either direction, would be one of the most significant scientific discoveries in human history. Conclusion. So here is what Jupiter actually is. It is not a failed star. It is a planet. A genuine planet of 318 Earth masses that formed within the first million years of the solar system, formed first among all the planets, carved the chemical structure of the protoplanetary disk, and then migrated dramatically inward and back before settling at its current position in a history that explains most of the peculiarities of the solar system's inner architecture. Its distance from stellar ignition is not a near miss, but a fundamental gulf. It would need to be 80 times more massive to achieve what it would need to achieve to be a star, and the solar system does not contain remotely enough material to build such an object. It is not a guardian. Its gravitational field is a blind mechanical force that scatters objects without preference for direction, delivering asteroids and comets toward the inner solar system as readily as it deflects them away. Its role in Earth's habitability is real, but fundamentally different from the shield narrative. It contributed to the delivery of water and organic molecules to the early Earth, shaped the architecture of the solar system that makes a habitable inner region possible, and possibly triggered the bombardment events that seeded Earth's chemistry. A complex, ambivalent history rather than a simple protection story. Its great red spot is not permanent. It is a dynamical state, maintained by ongoing atmospheric processes, shrinking on observable timescales, and possibly destined to disappear within the lifetimes of people alive today. Its interior is not a ball of rock surrounded by gas. It is a layered structure of molecular hydrogen, metallic hydrogen, and a diffuse dissolved core that challenges every pre-Juno model of giant planet structure. Its magnetic field is not a smooth dipole, but a complex, asymmetric, patchy structure generated by the convective motion of conducting hydrogen in a geometry we do not fully understand. Its moons are worlds: Europa with its enormous ocean and potential for life, Io with its violent volcanism driven by tidal forces, Ganymede with its own magnetic field and probable ocean, Callisto with its ancient cratered face. These are not accessories to Jupiter. They are, from the perspective of astrobiology and planetary science, potentially the most important objects in the solar system after Earth itself. And Jupiter has rings, faint, dark, dusty rings that almost no one knows about, maintained by continuous supply from small inner moons, visible only to spacecraft that fly through them or look back toward the sun. Rings that every planet in the outer solar system has in some form, because rings are not a special feature of Saturn, but a natural consequence of having small moons in orbit near a large planet. This is Jupiter, not the textbook version, not the documentary version. The actual planet, strange, violent, complex, ancient, and still full of questions that the best spacecraft and the sharpest scientists in history have not yet answered. A planet whose formation shaped the chemical conditions for every living thing on Earth. A planet whose interior operates at physical conditions that laboratories can barely replicate for fractions of a second. A planet whose moon may, in the single most important scientific question of the coming century, turn out to harbor life in an ocean that no sunlight has ever touched. You thought you knew Jupiter. You were just getting started.